RD. Now, I measure my output at node D, so the input is at the gate and the output is at the drain and the source is grounded. The source node S is grounded, and this is why we call this a common source amplifier. Okay, لأن الانput والoutput are using the other two nodes of the transistor. Okay, so when we studied this with the small signal model, we took the pi model for the transistor. This is the gate, node, drain, and this is the source. We have G and VGS here, and we have the little RO of the transistor, and this is really VGS. The way we would convert this such a circuit and study its gain, and what we did in 310, is that, well, here I don't have capacitors for simplicity. We would say that VDD becomes grounded, okay, and then we would try to bring in all the elements in red, attach them in the small signal analysis to the pi model of the transistor. So I would start with Vn. Vn is between G and the ground, but I know that my S node is ground, so Vn is really here. Okay, and then if I have RD, RD is between the drain node and the ground, so it will be between the drain and S in this scenario. Now the circuit is complete, so I can look and inspect, analyze what is the gain and what is my input and output resistance. Now, for gain purposes, the output VO is at the drain node, so the gain is really here. So the output voltage is between D and the ground, so this is really where VO resides, okay? So what would be the gain for this circuit? How do we calculate? What is VO على Vn for this circuit?
Minus G parallel RD.
Right, so we need to say VO is really minus GM VGS times RD parallel RO, right? Because the current, this current is flowing in this way in those two resistors in parallel, right? And this is parallel to RO, and this is Vn is nothing but VGS, so my gain, it comes out to be minus GM times RD parallel to RO, right? So this is the gain of my circuit. What's the input resistance? How do you define the input resistance? شو الانبوت ريزيستنس للسيركت؟ The input resistance Rn.
Vn over I.
Right, so In is whatever is delivered by Vn. So this is In here, right? And so Rn is really Vn over In, but In is 0 in this case, so it tends to infinity. لأنه I don't have gate current. The gate current is 0 in a transistor, and there's no elements connecting it anywhere. Great. And for the same circuit, do we know what RO is? For the same circuit, do we know what the output resistance is? How do we find RO?
We place Vx.
Okay, we place Vx. What do we do to calculate RO? RO من أول شيء صح بنحط Vx على Rx، بس شو بنعمل كمان؟ When Vn is equal to 0. يعني نحن we are going to put a Vx here. If we, let me erase this and state that it is RD parallel RO, because now you know that. So if I have this as RO parallel RD, okay, we're going to plug in a Vx here, Ix, right? and we're going to see what is the current that we see here when Vn is what? 0. يعني هيدا إذا صار 0 شو بصير عندي؟ بتصير الجيت is grounded or it is what? Shorted to the source لأنه خلص صار هيدا VGS is 0. لما VGS يصير 0 what that happens to GM VGS, the current source that is here?
Also 0.
Right, so if GM VGS tends to 0 at this condition بتصير open, right? لأنه it's a current source. So we will get rid of this one here. So this becomes 0. So what is the resistance seen by Vx in green?
RO in parallel with the RD.
Exactly. So this becomes equal to RO parallel to, little RO parallel to RD. Right? So this becomes little RO parallel to RD. Okay? So this is how we studied the common source amplifier in free time. Anybody has a question? يعني we're going to repeat it in the same context بس بدي تكونوا بس هيك refreshed شوي. Okay, طيب great. So now we can jump to the next slide and see, well, what happens if I remove the resistor. يعني I had a resistor RD here connected to the drain node. I had a resistor RD. I removed this resistor RD and I put in its place an ideal current source. أول شيء شو characteristics للideal current source? What is its effective parasitic resistance? The current source.
0.
ideal current source إذا بدي أعمل له modeling عادة بعمل له modeling إنه هو عنده parasitic resistance لإله parallel عليه. بس ideally do I want to load the circuit؟ لا، إذا كان ideal بس بدي أعطيه current ما بدي أخليه يشوف شيء resistance صح؟ so بدي يكون اللود اللي له infinity ما يسحب لا current ولا شيء صح؟ بدي إياه يكون بس يعطيني current ويكون هيدا resistance كأنه فعليا R infinity, right? So the ideal current source in small signal analysis, right? The ideal current source, right? In small signal analysis, what do we replace it by? نحن هو DC هيدا. قلنا they are set to 0. صح؟ Thank you إبراهيم. So they are set to 0. So إذا كان voltage بيصير short مثل ال VDD وإذا كان current بيصير شو؟ بيصير open لأنه عنده model of R infinity. Okay, so if I am studying the circuit now with an ideal current source in place of RD and I plug in the pi model of my transistor, I have GM VGS, I have RO, the current source is ideal, SAR open. Do I have any loading on my circuit? I don't have, right? I don't have any loading on the circuit. So now I can analyze the gain. I can analyze Rn. What is Rn?
R0.
Rn, looking from the input.
Sorry, yeah, it's infinity.
Rn is infinite. Ro, looking from here when the input is shorted, is really هيدي بتطير لأنه I shorted VGS مثل ما حكينا, so it is equal RO. And most importantly, what is VO over Vn? What is VO over Vn here in this simple circuit? إذا بدنا نجي نطلع
minus GM times RO.
صح, لأنه هاي هي minus GM VGS ضرب RO وال Vn here is equal to VGS. So بتطلع بتساوي minus GM times RO. طيب definitely this is greater than what I got before اللي هي GM-RD parallel RO. لأن أنا when I place a resistor, a pure resistor, I cannot make it too large. So this effective resistance, two resistors in parallel, where RD is small, okay, is definitely going to give me smaller gain, okay, than when I have an ideal current source plugged in here. Okay? So this means that if I don't load the circuit explicitly with a small resistance, my gain will be maintained. I will be able to maintain, actually, in this case, the intrinsic gain of the transistor. Okay, so let us look at what the slide is telling us here. يعني نحن عندنا لقينا ال Rn، لقينا ال Ro، ولقينا الجين، وقلنا إنه VO على Vn is really equal to the intrinsic gain of the transistor. So I recovered most of the gain, the maximum gain that I can achieve. So we want really to replace the resistor with the current source. What would be an ideal way? What would be, what did we learn last lecture? What can qualify as a current source? شو هو السيركت اللي تعلمناه اللي بيعطيني current that I can adjust?
The PMOS MOSFET mirroring.
الميرورينج صح. هلا لأنه أنا my circuit is below and I want to thank you يعقوب, and I want to put something between VDD and the output, I need to pick a current source اللي هي حتعطيني ال PMOS current mirror. يعني هي حتكون ال PMOS current mirror. So practically speaking, we're going to replace this by a current mirror. Okay, so كل هيدي will act like a current mirror and I'm going to interface it with my circuit. هلا for proper operation I need to guarantee two things. هيدا ليشتغل as an amplifier بده يكون بالsaturation region Q1. Okay, and the mirroring circuit, for it to do proper mirroring I need Q2 to be in SAT as well for proper mirroring. Okay, so for proper mirroring, I need Q2 to be in SAT. Of course, if we look here at the regions, and we're going to derive it in a second, if we look here he's showing me the total signal Vin, the total signal Vout. So this happens as a function of Vn, يعني as a function of the bias point of Vn, right? Because the bias point of Vn will really determine what the Q point or operating point will be, will determine VO, and from there we can determine إذا VO أكبر من VOV بالنسبة SD لهيدا أكبر من VOV حنعملها derivation. So we can determine if VO is greater than VOV for Q1 to be in saturation. We will derive it, but let us first look at this graph here. This graph, what it shows me is that, well, Q1 can be off or linear or SAT, but there's a region in the middle where it is saturation, and the Q2, it also has a region beyond which it is in saturation. So let us switch, I will switch to the iPad to derive those in the critical points that we care for, and we will discuss that accordingly. Yeah. Okay. So let me now. Sorry إذا عم يزعجكم النويز فوق, or it's okay. You can hear me well.
No, we can
Yes,
hear
you
you
can.
well.
Okay, thank you.
No, it's fine.
Type. Okay, so let us. Okay, so let us look now at this circuit. I have my transistor Q1 and I have transistor Q2 and the current mirror. The first thing that we will look at is what are the conditions for Q2 to be in saturation. What we know is that the voltage transfer characteristics will look something of this form. يعني as Vn increases, VO is going to drop because the transistor Q1 will turn on and it will pull down the output to ground مثل ما شفنا بالامبليفاير اللي هو هيدا common source amplifier. هلا for Q2 to be in SAT, the condition is that VSD for Q2, right? I want VSD for Q2 to be greater than VOV for Q2. Now, the first thing that we need to know about this circuit is when I reference is fixed, the current that flows in Q3 is fixed, and by virtue of that, the voltage point here, which is the common gate between the two transistors Q2 and Q3, is also fixed. VDD is fixed, صار عندي fixed VOV for this circuit. يعني I reference is going to determine VOV, and we'll take a problem about this later. So for Q2 to be inset, as function of Vn, Vo may vary, but we want to guarantee that this is satisfied, that VSD2 is greater than VOV, and we will call this 2 because Q1 also has its own VOV, and therefore Vs is VDD, okay, and VD2 is VO, and we want this to be greater than VOV of the PMOSes. Therefore, the condition is VDO is less than VDD minus VOV2. So we are going to determine a point here called point A, and this is what determines point A, where VO is equal to VDD minus VOV2. Anywhere below this point, I'm going to have Q2 in set. Okay, so as long as my output is below this point, Q2 is going to be in saturation. So this, we solve the first riddle. Anybody has a question? Great. هلا بدنا نطلع على Q1. Okay, so Q1, it is going to go through multiple regions. The first condition is very clear. If Vn is less than Vtn, the device is going to be off. يعني هيدي النقطة هون إذا this is Vtn, before this point the device will be off. Okay. هلا نحن we know that for the condition of Q1, for it to be in saturation, we want the output to be large, and we will want the output to be greater than Vn minus Vt, right? VGS minus Vt, because for this transistor, for Q1, what is VGS? This is VGS. It's really equal to Vn, which is Vg, right? And what is its VDS? هيدي D وهيدي S. VDS is also equal to VO, right? So the condition that says VDS should be greater than VGS minus VT really translates to VO greater than Vn minus VT, right? يعني إذا بيجي برسمه هيدا as Y greater than or equal to X minus VT, I can find a line that looks something like this. Okay, but I'm not going to draw it for you now. Let us see. Sorry, what is the edge of saturation? Where do I hit the edge of saturation? That's what I care for. يعني I know أنا for large VO, I'm going to be in set, so I will start here in saturation region, and then as VO becomes very small, somewhere here at some point B, I will hit the edge of sat, and the transistor is going to be in linear, right? لأنه بس تصير ال VO صغيرة, when VO becomes small, VDS becomes small, and a rule of thumb is that when this is small and this is large in a transistor, I will hit linear, and the condition is when VO is equal to Vn minus Vt. But if this happens at point B, يعني when VOB equal VNB minus Vt. So my task is to find when this happens, but first, if we know point B, ساعتها بأي region بيكون اثنيناتهم satisfying saturation. يعني The yellow is where Q1 is inset, okay? And the green below point A is where Q2 is inset. So where are both of them in saturation? Between points A and B, صح؟ نحن اتفقنا إنه when VO is less than VDD minus VO V2 هيدا حيكون بالsaturation Q1 Q2 صح؟ وهلا حنشوف إنه for Q1 to be in saturation I really need to be between ال VN يكون بين ال VTN صح؟ وبين ال VNB right؟ يعني let me rederive it, let us reconsider it. So okay, so up to point VTN Q1 is off, right? Q1 is going to be inset between this point here from the first time it turns on, as long as VDS is greater than VGS minus VT, as long as VO is greater than VN minus VT, and the edge of set point, okay, is going to be the point B where VOB is equal to VIB minus VT. Okay, when VO drops below this point, I hit the linear region. So below this point, I'm going to hit the linear region. Okay, فإذا Q1 is inset from the time it starts to turn on until it hits point B. Is this clear? Until it hits the edge of set and goes into the linear region. بعد ال VIB بيروح على linear, بصير Q1 is in the linear region. Okay, at point B, VOB is equal to VIB minus VT. Is this clear? يعني we have two transistors here. Okay, the first one, أول واحد يلي هو the first one which was Q1, okay, Q2 عفوا. And for Q2 حددنا الليمت له اللي هو point A وقلنا below this point my Q2 is going to operate in saturation ورجعنا أخذنا الترانزستور Q2 وجينا قلنا Q2 typically هيدا ال VO لإله وهيدا عفوا VN لإله وهيدا ال VO وجينا قلنا إنه هو حيكون بالأوف بعدين حيصير بالسات وعلى البوينت بي حيروح على اللينير ريجن وجينا قلنا انه هيدا الريجن اللي هون اللي عندي اياه انا هو what qualifies as عفوا هيدا Q1 sorry this is what qualifies Q1 to be in set and this is what qualifies Q2 to be in set. okay, فإذا في عندي نقطتين مهمين لإلي. Okay, point A below which Q2 is going to be in saturation and point B لأنه بينه وبين هي اللي بتحدد لي أمتى Q1 ببطل بالسات لما يكون داير بتفوتني على linear region. Is this clear? We have 2 points. Do you agree on that?
Sorry doctor, can you please just repeat really quickly لأنه ما كتير فهمت البوينت.
طيب let us repeat this. طيب بالنسبة ل Q1 let us talk about Q2 عفوا ال current mirror. Okay, let us look at the current mirror. For the current mirror circuit, okay, for the current mirror circuit, let me redraw it, that's the best way. Okay. For the current mirror circuit نحن قلنا إنه بدي أنا عندي transistor Q2 صح؟ And we said that this gate voltage is fixed by virtue of I reference صح؟ And this fixed I reference is going to give me a solution for VOV for transistor 2 and 3 صح؟ Okay, now I have transistor Q1 that is trying to operate with these devices عم بغير لل VN I have given, and I know that as Vn increases, it's going to pull the output down by virtue of the behavior of a common source circuit, and this is Vo. Okay. The first condition that we want to address is for Q2 to be in saturation. For Q2 to be in saturation, I want to satisfy that VSD2 to be greater than VOV لQ2. هي أنا معيها. It's a known value. So this tells me that this is VDD minus VO, مش هيدي ال S وهيدي ال D لQ2. It should be greater than this VOV2, and therefore this tells me that VO should be less than VDD minus VOV23, right? So if this is the point A, which is VDD minus VOV2, any value of Vn that gives me the output below it is going to guarantee that I am biasing Q2 in saturation region. So كل هيدول ال Vn بيضمنوا لي إنه Q2 is in saturation. Is this point clear?
Yes.
Okay, great. هلا, the second thing that we need to worry about is when Q1 is in saturation. So أنا إذا بدي أرجع أطلع على transistor Q1 وجيت درسته in the context إنه I have here, this is the current mirror, okay, and this is my transistor Q1, it's sitting here, it is being biased by Vn وعم يعطيني some VO حسب الانتراكشن بين التو circuits. وهيدا شكله للcharacteristics، هيدا شكل الvoltage transfer characteristics V in versus V out. We agree that it is going to look something like this. I want now to divide this into regions. The first thing that I will study is that Q1 is going to be off لما VGS أقل من VT, but for Q1 I know that VGS is equal to Vn, right? لأنه هي من هون لهون. So هيدي بتصير لما ال Vn أقل من VTN بتكون الديفايس شو هي؟ off. يعني I cannot have any current flowing through the transistor حيكون مطفي. Okay? طيب. Now, what we know as a rule of thumb for any transistor, if this is its drain and source, إذا هيدا هو NMOS, okay, لما ال VDS تكون أكبر من VGS minus VT, يعني as a rule of thumb, if this is large and this is small, then I will operate in what region?
Saturation.
Saturation. So, the intuition tells me that لما بعده الأوتبوت بالأول عالي high and Vn just turned on بعد شي exceeded VTN, the chances are it agrees with the fact that the device is in the saturation region. So for the input beyond VTN, I start in sat. As the input is increasing and the output is decreasing, as my output VO, which in this case represents VDS as well, and هيدا drain وهيدا source for me, this is the drain and this is the source, okay, as it becomes small and as the input which represents VGS becomes large, يعني as Vn increase, VGS is increasing and VO decrease, يعني VDS is decreasing, I'm going eventually to hit the linear region. Right? And if VO becomes 0 or 0.1 and Vn is VDD, I'm definitely in the linear region, right? Now, there exists a point in between the saturation and the linear, between VTN and VDD, لما هيدا بصير كتير high, I will call it point B, and at this point B, I'm going to try to find the edge of saturation solution. يعني what is this point B? So our objective is to find the point B, which is the edge of sat. Okay? Is this clear?
Yes.
Okay, so we want to find the point B, which represents the edge of SAT. We know that at this point B, if I am operating at edge of SAT, I will have VIB and VOB, and they will have some property between them. Okay, so at B, okay, if I will have VDS1 equal VGS1 minus VT, so this I will have VOB equal VIB minus VT. So how can I solve for this point? Let us look at the circuit. So let us look at the circuit to see how we can solve for this point. So at point B, if I want to solve for B at edge of SAT, I have my circuit. This is Q2, this is Q1, Q3 F1, هيدي I reference, and this is my VN. Okay, and at this point, I know that I have VIB. Okay, so I will have VIB here, and I have here VOB, and I want to solve for the current. So how do I solve for the current? I will need to say that IQ2 is equal to what? IQ1, right? So if I say that IQ2 by virtue of KCL is equal to IQ1, I know that IQ2 by mirroring, I can derive it as half K prime W by L VOV 2 square. If all the sizes are equal, it will be equal to I reference, okay? And as far as transistor Q1, if it is at edge of SAT, then we are going to say that the current IQ1 is equal to half K prime W by L1 times VIB minus VT square times 1 plus VOB over VA. Okay, let us say that this comes out to be equal to I reference. Okay, then I can equate that this is equal to I reference. Can I solve for VIB and VOB now?
Yes.
Because I know that I can plug in place of VOB, VIB minus VT, right? So I can find the edge of SAT point, right? Okay, so now, and we'll take a problem about this. Now what we have is we have a first point for Q2. Okay, so this is Q2, this is VO, this is VI. That tells me below A, I am going to be in saturation. Okay, and I also have another curve and another point for Q1. Okay, that tells me in relation to Vin and Vout, okay, I have 2 points that matter for me. The first point here, VTN, and the second point is point B, okay, so this is VIB, and in between those 2 points, the transistor is operating in saturation. So هيدا بين ال VTN وال VIB, وهيدا they happen to be, if I map them here, this is VTN and this is VIB, and if I bring this here, then the common region, if this is point B, is really between points A and point B. Yani point A gives me an upper bound on VO, okay, and point B gives me a lower bound on VO. هيدي I obtain it from Q2 condition to be in SAT, وهيدي I obtain it from Q1 saturation condition. Okay, يعني أهم شيء in a given problem, if I know that those 2 transistors are going to control my performance, I need them both to be in SAT. Each one of them, if I write the saturation condition for it, is going to create for me a limit 1 bound on V out. Is this clear now?
Yes, all good.
Okay, excellent. طيب هلا we will go back to the slides. Now we'll go back to the slides and we will see what we have there. Okay, so let's come back to the slides. Let's share the screen 1 second. Sorry. Okay. So let's come back here and let's see what we have here. So here now we know that between A and B, sorry, between A and B, we have this region here, region number 3, that where the two transistors are in saturation. This is point A, this is point B. هي الedge of sat ل Q1 وهيدي هي saturation condition ل Q2. Okay, and I need to guarantee that I operate between those 2 points. Great. So if I want now to perform a small signal analysis of the CMOS common source amplifier now, if this is a transistor Q1, okay, and this is the pi model for Q1, I want to now plug in the effect of this whole block on my circuit. If you recall, when we studied what's the output resistance for the current mirror, we said delta VO على delta IO equal RO, and the effective loading is really RO2. Yani if the current mirror is interfacing me through Q2, then this whole circuit can be really replaced by a simple resistance RO2 يلي هو between this node and ground. So I'm going to plug in at VO in place of all of this current mirror a resistance equal to RO2. هلا بنعمل derivation a little bit later. We're going to derive this, but with respect to this circuit, what does this mean? This means that at node VO, I will plug in another resistance RO2 to model my current mirror. Okay, to model my current mirror circuit. Okay, so a small signal equivalent of this big circuit is RO2. We're going to plug it in here. And now can I study what's the gain, what's Rn, what's RO for this circuit?
Yes.
It should be simple for us, right? So Rn is infinity. RO is really those two in parallel, right? Because we're going to short this to 0, this will go away, and we will see RO1 parallel to RO2. And the gain is really VO over Vn, يلي هي minus Gm VGS times this parallel over VGS, which will be minus Gm RO1 parallel to RO2. This is still greater than putting an external resistor RD and making it in parallel with RO1, because RO is typically decently large. Okay, يعني هيدي كأنه if they are equal, it's as if I divided the gain by half, but I did not make it smaller than this. Okay, so this is the advantage of the current mirror. It's really helping me maintain my gain, keep it of the same order. Okay, حدا عنده سؤال على هذه slide? Anybody has a question?
Professor, can you say again, please, why we were replaced by R02, RO2?
Okay, so let us assume on chip, if we want to put RD, which is external, it will take a very large area if I want to make it very large. So let us say RD, which is reasonable, is 1 kilo ohm, for example, just for heck, to make it an extreme case. And let us assume that RO1 and RO2 are both equal to 20 kilo ohm. If I have the gain through this circuit, I will have minus Gm 20k parallel to 20k, right? And if I have RD, I would have had a Gm into 1k parallel to 20k, which will give me a higher gain, which is a larger resistance, 20k parallel to 20k, which is 10k, or 1k parallel to 20k, which is going to be less than 1k, which is a larger resistor.
20k.
20k parallel to 20k.
So this really maintains my gain compared to minus Gm times 20, لو ما كان عندي load أبدا بالideal case, whereas this really can choke my gain. So I prefer to use on-chip current mirror because it helps me within the same small area obtain a decent gain. Otherwise, I need to use a large area to get a higher RT. Okay?
Okay, thank you.
Okay, thank you. طيب great. Hello. Let's see now what happens if we why the model is RO2, but let us see first how we can approximate this. Yani every time I see this circuit, I don't really have to carry it over and keep drawing it with me. In reality, this whole thing is really equivalent to this point, as we said, by virtue of I reference. What happens to VOV? It is a constant. If we know what I reference is, VOV23 for those PMOS devices, it's a constant, right? When I solve I3 equals to IREF, if this is DC, I get a solution for VOV, right? Let us say for 1 milliamp, I get VOV, let us say 1 volts. If VOV is fixed and VDD is fixed, what is VOV in the end? This is VSG minus magnitude of VTP, which is equal to VDD minus VG minus magnitude of VTP. If this is known and this is known and this is known, would VG be fixed or not? And if this is 1 volt, then I know what VG is. Then VG may be, let's say it is 2 point something, okay? So then this is a fixed voltage. So a fixed IREF is going to determine for me a fixed current that's flowing and a fixed gate voltage. So it's really as if I have a bias here. It's equivalent, the current mirror is equivalent to plugging a DC value here that will result in a, when Q2 insat, in a constant or almost constant current Q2, right? Corresponding to this specific VOV, right? So I can replace this whole circuit by an equivalent V bias, okay? And now we are going to look at a rule that says if I have a transistor with a DC voltage at the gate and a DC voltage at the source, the resistance seen looking into the drain is equal to the little RO. But let me explain this on the next slide. So let me explain this to you, and then we will look at it from the slides. It will be clear for you. So if I have a transistor, independent if it was NMOS or PMOS, but let us take it from the NMOS and we will use it as a rule. If the gate is at DC and the source is grounded and this is the drain, and I'm trying to see what is the effective output resistance or the resistance seen looking into the drain. Let us see if we draw this model here for this transistor. This is the pi model. I will have here GM VGS, okay, and I have here the source grounded and the gate, and I have the little R. What does it mean to have the gate at DC? What is the voltage at the gate in small signal analysis? Ground,
zero. Yeah.
right? So what happens to VGS now? So the gate with source, both VGS are 0, يعني VGS is equal to what? 0, right? If VGS is equal to 0, what happens to the current source GM VGS times 0? A current source with magnitude equal to 0 is really what?
An open
Is
circuit.
an open circuit. Great. So if I bring a supply here Vx that is going to interface my circuit here, the resistance seen looking into the drain, this is the drain node, looking into the drain node, what do I see? What is the resistance that I see looking into the drain node?
R0.
I see RO. So if a transistor has the gate biased at DC and the source grounded, looking into the drain, the effective resistance is really RO of the transistor. Okay, so we will see it on a slide. Let us go back here. Look at this circuit that we just saw with the V bias. Okay, this transistor here has the gate at DC, the source node at DC, and I'm really trying to see if I look into its drain. If I look into its drain, what do I see? In small signal analysis, I see an effective resistance equal to what?
R02.
R02. Okay, so these are rules. I will show you next time the resistor sheet. These are rules that we will start to look at. If I come and tell you now, let us look at this common source amplifier and its version on this right-hand side. And I want to know what is the output resistance of this common source amplifier, right? The output resistance is when I put a supply VXIX, okay? And what do I do to the input? I ground it, right? I ground the input. I set Vn equal to 0, right? We find RO and Vn equal to 0, and it is equal to Vx over Ix. Let's see the current Ix. Where is it going to? It's going to split into two branches. One looking into a transistor Q2, okay, with the gate and the source at DC, right? And another one looking into transistor Q1 with the gate and the source where also at DC or ground. So the resistance seen looking, if the current is being added, if Ix is equal to I blue plus the current which is in green, right? The current that is going in I down and I up, if we want to call it, then the effective resistance is going to be in parallel. يعني أنا if I put an I and I look into transistor Q2 with this at DC and this at DC, what do I see? What resistance do I see? We just derived it. We see RO2, right? Looking into the drain, up into the drain with the gate and the source grounded, we will see RO2. So looking this way, and we will derive it all next time. بس حبيت هيك بس خليها براسنا قبل ما نوقف الصف. Keep it in our mind. Looking up, I will see RO2. Now looking down from this node into this transistor with the gate and the source grounded, what do we see? From the drain, looking down into the drain, I put somebody at the drain, looking down into the transistor, peeking at the transistor. Somebody's eye is here and they're looking at the transistor with the gate and the source grounded. What do I see? RO2 or RO1? RO, right? I will see RO1. صفى هيدا ال VX. If he's sending a current or sending inspectors who are branching, looking into two drains connected at the same node, one way up he will see RO2, and one way down he is going to see RO1. What is the effective resistance seen from this node? إذا عندي نود عليه ريزستور RO1 وعليه ريزستور RO2 اثنيناتهم بين this node والground, what's the effective resistance?
RO1 parallel.
The parallel, okay? So we will derive it next time, but I will show you the resistor sheet, and I want you just to keep in mind that we will start to deal with the transistor as a block. We see what node we are looking at, what nodes are fixed, and we can use the rules for this. It will become clearer next time, don't worry, but we will stop here now. Okay, anybody has any question?